like to give a few pieces of advice on the homework assignment. Let's look first at the homework assignment 2. And I have here on this figure, as you can see, problem that we want to calculate a few of the parameters relating to a single crystal. So what I wanted to say is that this problem was on a quiz, and in this problem I have a plane, and the plane, as you can see, is actually cutting the crystal at distance a from the origin along the x direction, and the distance a also from the origin along the y direction, and then 2a along the z direction. So we can call x as x1, y as x2, and z as x3. And we have an applied stress along the z direction at 50 MPa. The idea of Miller indices is that first we take the intersections of the plane with the three directions. So the intersection here that we have, let me just get this here. See, the intersection on the x1 is A, and the intersection on the x2 is A, and the intersection on the x3 is 2A. And then after that, we take the inverse of these intersections and take the unit of the crystal structure A out of the equation and form the Miller indices of that plane as the integer multiples of these inversions. So to make my point clear, here is the Miller indices of the plane. We took the intersections and we inverted the intersections. So I have 1 over A, 1 over A, and 1 over 2A. Then we take the A out because it's just a unit of measure, and I will have 1, 1, and then 1/2. Now, to find the indices for the plane, then I have to multiply by a factor of 2, and therefore I have the Miller indices of that particular plane will be 2, 2, 1. Now, what's important is that the normal vector to the plane is identical to the Miller indices of the plane itself. The only thing is that if I want the unit normal, then I have to normalize the vector. Normalizing the vector means that I just divide by the square root of the magnitude a squared plus b squared plus c squared. So it's like a Pythagorean theorem that I applied so that I can get the magnitude and normalize the value of the vector to that magnitude. So if you looked at the unit normal vector to the plane, it is 2 over 9. You kind of highlight that if I can. So I have 2 over 9 and 2 over square root of 9 times 1, 1, and then 1/2. I should basically multiply by 2 everywhere, so it'd be 1 over the square root of 9 times 2, 2, 1. So whenever you have a problem that has a plane, you can follow the same procedure to find the Miller indices of the plane and to find the normal as I outlined in here, and it's important to have the unit normal, so the magnitude of that vector is 1. Then this problem is that we have now an applied stress of sigma of 50 MPa along the x3 direction. So if I want to represent this as a vector, then the applied stress would be 50 in the k direction. So the k direction will be the vector along the third component of the Cartesian vector. Now in this problem, what we wanted to do is we wanted to find the normal stress to that plane, and we also wanted to find the shear stress along a vector on the plane called S, this vector here called S. And the vector S is given graphically. So it is our job to find the direction of that vector, or what it is exactly. And we have to find it in a normalized way. If you look at that vector S, then it's obviously that this vector is going 1 unit along the x1 direction, but if you look along the x2 direction, it's actually going a -1 unit along the x2 direction. And then if you look at the x3 direction, it is basically going 0 units along the x3 direction. So what I can say is that S here is equal to 1 unit along the x direction minus 1 unit along the y direction, and then 0 along the z direction. So this is a vector S, but it is not normalized. In other words, its magnitude is not 1. So I have to take that and then make the magnitude equals 1. And then what I did is in the S vector is 1 over the square root of 2, 1 bar 1, 0. Finally, the third vector that is important in this problem is the vector that is aligned with the load, the L vector here, this L. And the L vector is obviously equal to 0 along the x, and then 0 along the y, and then 1 along the z, and I don't have to normalize because it's already normalized to unity. Then I'm ready now to do projections. Projections is that first is L dot n will give me 1 over the square root of 9. L dot s will give me 0. Note here that L dot n is really the cosine angle between the two vectors L and n. And L dot s is likewise the cosine angle between the two vectors L and s, and obviously this is 0, so they're normal to one another. So what we can say is that the Schmidt factor SF is actually, this is cosine lambda and this is cosine psi. If you remember from the notes, we had the cylinder and we worked out the geometry as cosine lambda and cosine psi, and then we're multiplying that together, then we get the Schmidt factor. And then you multiply now the load by the Schmidt factor to get the critical result, shear stress. And as you can see here, because L dot S is equal to 0, you get really 0 shear on that plane, which is very interesting. On the other hand, if you're looking at the cleavage or normal stress on the plane, then you take sigma times cosine psi square, which is L dot n square. Okay. I wanted you to compare that to the figure that we have in the notes. We have a lambda, which is the angle between the loading direction and the slip direction, and we have psi, which is the angle between the loading direction and the slip the normal to the slip plane. And those are the ones that we have in the notes in case we have a cylinder. So now all of this, what I'm talking about here is that you have two types of problems. One type is that you have actually a cylinder, very well defined, and you have two angles, lambda and psi, and from those you can obtain the normal stress on any given plane, such as this plane here, and also the shear stress on that plane along. Notice that the shear has to be along a given direction, slip direction. So this is one type problem. The other type is when you have the crystal, and the crystal is defined by, you have a plane on the crystal, and then you find the Miller indices, and you find the normal vector to the plane, and you find also the shear vector S on that plane. So that we'll stop here.